going to discuss about the thrust number 2. In thrust number 2, in our projects going on within the Dependable Computing Systems Laboratory, we are considering the problem of debugging really large-scale distributed applications. So the goal here is to provide applications which are distributed, running on multiple machines. Oftentimes these machines are distributed over wide areas, and run these applications in a way which is dependable. And this involves in our work two fundamental primitives. One primitive is to perform failure prediction. So before the failure actually happens and becomes visible to the end user, can you predict it and therefore take some proactive steps so that the failure does not become does not impact the overall running of the system and create an outage. And another aspect of it is perform automatic bug localization, or localize where the fault lies so that a correctly functioning component can be replaced. The challenges that occur in applying these principles, developing these principles for today's distributed systems are threefold. Firstly, you have lots of different entities over which these distributed applications run, many machines, many heterogeneous machines, and they consume large amounts of data. So any technique that you come up with really has to be scalable in both of these dimensions, large number of entities and large amounts of data. Now, because there are all these different entities, software components running on hardware platforms, interactions between these software components cause error propagation. So for example, an error in component 1 may actually manifest itself as a failure in component 2. And components 1 and 2 may be separated far in terms of their interaction distances. And while building any dependability protocols, we still have to keep in mind that these applications will have high throughput and low latency requirements. So one sample project that we have within this thrust is for cellular networks. And for cellular networks, when the amount of data or the number of devices that are connected to a particular base station, and E node B in the 4G architecture, how are you able to handle these large failures that occur because of this large scale? So in this project, which is joint with Georgia Tech and AT&T Labs, we are considering the problem of building machine learning models using offline data to understand what are correct interactions and what are interactions which are predictive of a failure that's going to happen in the near future. So with this wealth of information that's collected in today's cellular networks and the E node Bs, we can create these offline models. And then at runtime, these offline models can be queried to answer the question, is there going to be a failure or a degradation in the data throughput in the near future? And if there is, then certain mitigation actions can be taken even in the current cellular network context. For example, one mitigation action could be to pre-download, to pre-cache the necessary content that's going to be used in the near future in anticipation of a failure, or to disconnect the device from one E node B and connect it to a different E node B where the chance of a failure is reduced. Another aspect of work in this thrust is metric-based bug localization. So today's distributed applications running on large numbers of machines collect a lot of information from the entire software stack on these machines, starting from the hardware level information like CPU performance counters, going up to the operating system, what is the utilization of the CPU, the memory, the I/O, the network, to the middleware level. For example, if you're running in a virtualized environment, what are the numbers of virtual machines, what are the numbers of containers, and what's the utilization for each virtual machine or container. And all the way up to the application level, where, for example, if you're running a database server, you monitor what is the throughput that you're getting in terms of read rates and write rates. So the overarching problem in this space is, how do you use this wealth of information this deluge of metrics that are being collected on a regular basis, either periodically with a fairly short time period or in an event-driven manner, where in case of certain anomalous events, certain monitoring is triggered. So how can we use all of this information in order to localize the root cause of the problem? So the state of the art as well as state of practice would be to look at individual metrics and to say if this metrics pattern deviates from what is a nominal pattern, you would flag this as a problem. And that does take care of lots of the common kinds of bugs or hardware malfunctions that show up in practice. But for the remaining 10% of the very hard to localize bugs, we find that you actually have to look at multiple metrics and correlations among these multiple metrics. So under normal execution, these correlations follow a certain pattern. Under abnormal execution, these correlations break and deviate from this pattern. So one recent area of work in this space has been in approximate computing. So approximate computing holds the promise that you would be able to execute your application while minimizing the amount of time or the amount of energy that is needed to execute the application by cutting corners, by executing this application in an approximate sense. While it does save resources, one question that the community has is if something goes wrong, so maybe my results become inaccurate or the performance improvements that I was expecting don't materialize, how can I go back and pinpoint this to either an incorrect approximation or too aggressive an approximation? And we have developed some techniques in order to do this kind of a root cause analysis for approximate computing programs. And this is joint work with the University of Illinois at Urbana-Champaign. Yet a third piece of work in this space is debugging problems which show up at extreme scales, at very large scales in terms of the number of processes, for example, the size of the Hadoop cluster and the number of the map and the number of reduced processes that are running on your Hadoop cluster, or in terms of the amounts of data. So for example, we work with computational genomics applications where the amount of genomic and metagenomic and epigenomic information has grown to a huge level, where the amount of data that these applications are run at really are much higher than what these applications were tested on. So these correctness or performance problems do not show up at small scales, the development scales, the testing scales, but they do show up when they're thrown out into the production cluster and made to operate on real production data. And current debugging techniques, including statistical profiling techniques, are unable to handle such kinds of problems, because current debugging techniques or statistical profiling techniques have this fundamental premise that if you think of the light green as our training runs and the dark green as the production runs, in the case of statistical analysis, it will flag the light green training runs. It'll infer a certain pattern from these light green training runs and try to see if the production runs match that pattern. And if it does not, then it will say that it's anomalous. So in this case, two of these production runs would be called anomalous and one of them would be called correct. But in reality, if you take into account the scale, you would find that maybe the production runs that were flagged as anomalous are actually correct and the other way around. And this intuition comes in is that if you take into account the scale, the behavior of your application follows certain pattern with the scale. And so in this thrust, we are looking at debugging problems in distributed applications at various different kinds of scales and various different domains.